Okay, this is the video cast for section 5, problem number 2, and in this section we're talking about the Stern-Gerlach experiment. So let's take a minute to discuss what the Stern-Gerlach experiment was. This was one of the experiments that allowed us to determine the spins of an electron. You took a stream of silver atoms and you shot them through a large magnet. But what you can do very precisely with magnets is measure what the magnetic field is at different places between them. So for this magnet, the magnetic field happened to vary along the z-axis in a linear fashion. So the magnetic field at any point can be called B plus B0, B0 plus AZ. We discussed in the introduction, which is on the problem 1 video, that when you have a varying magnetic field, charged particles are going to feel a force. And indeed, that's what happens here. Particles that are experiencing the upspin feel a force that causes them to move upwards, and particles that are spinning in the down direction feel a force that causes them to move downwards. And in this problem, we're going to do a few calculations to see why this is. So question A is just a conceptual question. You have an electron, it's spinning in its hydrogen 1s orbital. Does it have the same energy if it's spinning up as if it's spinning down? And the answer to this is no. We learned in the last problem that the energy is equal to the gyromagnetic ratio times the spin, and the spin will have a different sign if it's up than if it is down, leading to a different energy in both of these cases. The gyromagnetic ratio times the spin is mu, the magnetic moment. To get the energy, we also have to consider the strength of the magnetic field. So let's take a moment to plug some numbers in. We want the energy splitting of both a spin up and a spin down electron. So what's the energy going to be for a spin up electron? Well, just as it was before, it's going to be the gyromagnetic ratio times the spin times the magnetic field. And we want it to have a lower energy if it's aligned with the field than if it's not. So we're going to stick a negative sign in front to ensure we get that result. Now we have a value for the magnetic field and the spin. The spin is just h bar over 2. It's positive because this is our spin up case. And our magnetic field is some B sub 0 plus AZ. We can solve the spin down case in a very similar way. The only difference is now you have negative h bar over 2 because you've changed the direction of your spin. And we want the energy splitting, so the energy difference all of those terms end up canceling out, and you're left with just this extra negative sign from up here. So you end up finding, much like we did before, that your energy splitting is going to be the gyromagnetic ratio times Planck's constant times the magnetic field, where we now have this expression for the magnetic field. Okay, so for part 3, we want to look at the force on the electron. Recall that the force is just going to be the change in energy divided by the change in position. We calculated the energy in the last part. For the electron with a positive spin, it was negative gamma h bar over 2 which, once we take the derivative, we lose this z here, and we're left with gamma h bar a over 2. For the up electron. For the down electron, it's the same formula, we just have an extra negative sign. Which leaves us with a force of the same magnitude, but in the different direction. And it's these forces that allow that Stern-Gerlitz setup with the two magnets to separate the spin up and the spin down particles. So now let's assume we have a homogeneous electric field. So it's not the magnetic field equals B sub 0 plus A sub z. It's just B sub 0 over the entire space. You can also think of this as just assuming that alpha is 0. So the energy is still going to be different, right? Because you still have the energy is equal to the gyromagnetic ratio times the spin times B sub 0, and the spin can still be either positive or negative. But you're not going to see a difference in the force, because when we go to take those derivatives from up above, now there's no z term. Everything looks like a constant from the perspective of that derivative, and you don't end up seeing any force as a result.